Manil, something I often think about. This is a question I think is best for you, and it's why is mathematics, something invented by humans, so universally applicable to the reality around us?
Well, that's a very difficult question. It's something that's been debated maybe all the way from Plato, certainly all the way from 1960 when the Nobel Prize winner Eugene Wigner talked about the unreasonable effectiveness of mathematics. And what he was saying was, hey, this is something made up by humans. And why does it keep popping up? Why does it explain nature so well? Why does it explain physics so well? And there's no complete answer to that question. People have, managed to whittle it down and give various examples and so on. But it's one of those mysteries of mathematics. And by the unreasonable effectiveness, what I mean is things that were, mathematics has been around forever. Think back to the ancient Greeks from antiquity. They came up with conic sections, for instance, and ellipses and so on. And, various things in geometry. And then years later, ellipses, for example, were used by Kepler to figure out how planetary motion works. Now, why would something so abstract and so unrelated happen to actually have an effect on something so real for us, so directly out of nature? And this kind of thing happens over and over again. I mean, I can give you many examples. A big example is group theory, completely abstract. Looking at mathematical structures. It certainly helps describe symmetry very well. And that's why, again, decades later, maybe a few centuries later, in fact, in terms of quantum mechanics, the way that particles are distributed, the symmetries that one sees in that, they turn out to be very nicely described by quantum theory. By group theory, I'm sorry. The one thing that I use in my book is how these so-called non-Euclidean geometries or curved geometries. The simplest example is just a sphere, but these curved geometries, they do not follow the rules that Euclid laid down, again, many years ago, many decades ago, centuries ago. And these were, again, completely abstracted by people like Gauss and a whole bunch of Russian geometers who, in the 19th century, started examining these things. What would happen if you created what parabolic geometries or elliptic geometries where space is actually curved? And again, they were something that completely abstract. These people had no idea and no desire to really apply them in any case. And then along comes Einstein, maybe 60 or 70 years later, and figures out that, hey, this is the perfect thing to explain gravitation and show that our space-time is actually curved. So, that's the mystery in all of this.
I think you do such a fantastic job at explaining all these complex phenomena in your book. And I'll put a link to that in the description. But over the years, you've also done so much work within the fiction side of life. I mean, you found a great way to fuse these two hobbies / jobs of yours. How do you think you've been able to do this so successfully as a novelist and a mathematician? I mean, these are very diverse and different fields. And
I agree that they are different, but and that's what's got me started because okay, when I was first started as an assistant professor, I was told, hey, you need to really concentrate just on mathematics, otherwise people won't think you're serious and so on. And so I was very careful to put my nose in the book. Another dimension, sort of like what you have. You're doing this, even though you do medicine and so on. So I
Mm.
think we all can benefit with something that's completely different. I had to be very careful. I wanted to get tenure, so I was completely tight-lipped about this. I used to live in Baltimore, but I used to go to Washington to go to a writing group there, and started doing fiction, writing fiction just as another dimension, as something completely separate from my mathematical life. And I started really getting into it, into my first novel, which is The Death of Vishnu. And, one summer I went away to a writing colony, but told everyone at school, hey, I'm working on a calculus book. And when I came back, they asked me, can we read it, whatever? And I said, no, it didn't go well. I'll have to go again next year. So it was the first time people really found out about it. Was an excerpt was published in the New Yorker the year before my book was released. And so there was a lot of surprise that I'd been doing this, but it was a lot of fun because it really got me meeting people that I wouldn't have otherwise. So I think that was the biggest thrill of all.
Mm. And I mean, there's clearly a theme. I mean, even in your trilogy, I mean, Death of Vishnu, and then you got your book, Big Bang of Numbers. There's this overarching element of the greatest story ever told, which is the universe and its creation, or its design. I mean, the word design doesn't really work well in this context, but is that something that intrigued you from the very beginning? Just this bigger picture?
Well, I think the Vishnu idea came because there was an actual person named Vishnu who died in my building. And so that was the spark that really started that book. And I was just going to write something, kind of about the building and its inhabitants and so on. And then I was taking a writing class, and the instructor said, hey, if you're going to name your main character Vishnu, that's a loaded word because Vishnu is in Hinduism, he's the god of, he's the caretaker of the universe. So you can't just call him Vishnu and let it go at that. So that's when I started looking into things and tied it to this idea of caretaking of the universe, how it's built. So the building becomes a metaphor
Mm.
for the universe. And then Vishnu becomes its unofficial caretaker, which he was in real life. So that's what got me started on this. And then, of course, the second book, well, Vishnu, Shiva, and Brahma, they form a trinity in Hinduism. So I thought, hey, it's a good idea. I'm going to just write a trilogy. And I told that to my agent. And then I thought maybe, that's really committing myself too much. I need to go back to my math. And I told her, don't tell any of the publishers yet about that. And she said, no, 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 I have told all of them. So you are writing a trilogy now. So I did write The Age of Shiva, which was the Shiva is the destroyer, and it was very metaphorical in that. And then when it came to Brahma, who's the creator, I realized that he's not really someone who has the same kind of worship, number of worshippers as others do. And really, it's Devi, the mother goddess, who is the third part of the trilogy in terms of how many followers she has. So that's what became the city of Devi.
Mm.
And after that trilogy was complete, I said, okay, now I can finally finish with this and go back to mathematics. And lo and behold, it turned out to be something that the book that you're reading now is very different from what I started with. I've been working on it for 10 years, and it went through 3 iterations. And I don't know, I guess I'm just obsessed with this idea because, again, it turned out to be about about the universe and about creation and all these deep questions.
Mm.
And it was really great to be able to look at it first in terms of mythology and now look at it in terms of mathematics.
Mm.
And the intersection between these two, the religion and the mythology, that was great too. Seeing how it interacted with mathematics. And and there are various coincidences that occurred. Like one of the things that I described in the beginning of my book is that it followed originally from an article I wrote for the New York Times. And this article did very well, and it was, most emailed for the day. Then it became third most emailed for the week, second most emailed for the week. And I was just poised to be the first most emailed for the week. This was on a Saturday after it came out. And suddenly the Pope started making these very progressive statements about abortion and homosexuality and so on. And he came bounding from behind me and jumped over me and landed in my #1 spot. Uh, so, as revenge, perhaps, not as revenge, I'm happy with the Pope. I even sent him a copy of the book. But I thought, okay, why not make him a character? So he ended up being a character. And this Pope is very interesting because he actually worked as a chemist for a while in his early career. He worked in a chemical lab. So he has this connection with science as well. So I constantly used him as a mouthpiece to see what the difference was between the religious side and the mathematical side, the scientific side, and perhaps the miracle side, if you like.
And tell me, in your life growing up, was there ever a point where you were religious, or did you felt like you did commit to a sort of religious doctrine?
Oh yeah, my father was very religious. Plus, I went to a Catholic school, and so we had our prayers and all, and I would do all that every night. And then around 15 or so, I just kind of decided my mother was always more atheistic. So I said, I'm going to just forget about religion. I'm going to be a complete atheist. And then I guess being a mathematician, I thought, interested in mathematics, I thought maybe that's too severe. So let's be an agnostic.
Yeah.
So I modified my stance. So I haven't really, since then I haven't really been religious in the traditional sense. The first book, The Death of Vishnu, I had to read various texts like the Quran and the Bhagavad Gita, and that kind of the spiritual aspect of that I found very interesting and very calming. But other than that, no religious beliefs as such. But the mythology aspect is very interesting to me.
I find it's very intriguing how that happens to quite a few people, where they sort of leave that religious dogma and then slowly go through this hardcore atheist phase, and then eventually transition back into a sort of spiritual kind of quasi-religious view of the world. And it's usually something like science or mathematics that grounds this spirituality at some point. And you do this with mathematics. Why do you feel that is? Why do you think that's such a common pattern?
The kind of in and out of religion?
No. In general, the way we were able to ground mathematics and science, because I find I'm very similar in that regard, is the more always talk about the universe, the more it is sort of religious to listen to this story. I mean, this mathematical story of the universe, it is quite awe-inspiring.
Yeah, it's very interesting because it's one of those things that we are unlikely to get a complete answer from any one source. So I certainly would like to believe all the stuff that scientists have come up with, that physicists have come up with, the Big Bang and so on. And I think that's, a rough model of what might have happened. But you always have this problem of you can keep going backwards and keep asking, well, what was there before that? Or who created that? Or how did that happen? And so it's a never-ending chain, and you can't really go back to ground zero. It's ground minus infinity, essentially. So I think that's where the mathematics might actually, tell us something, which is that in math you always have to start with some axioms. So you always have to start with some assumptions, and the reason for that is simply you have these terms like perhaps it's a set or a number or a point, and these are undefinable terms in the sense that you can't break them up any further, because otherwise you'll keep describing things in terms of other things, and then you'll have to define those and so on. So mathematicians, logicians especially, they're built up mathematics starting with axioms. So you have to start with some assumptions. And so that's the kind of reassurance almost that you can grab at as a mathematician, that, okay, I'm going to start with this set of assumptions and that's it. And I'm not going to go any further trying to look at where those came up with. So I think that's, once you take that into account, then you can start building up things. Like I start with numbers, building it up from the empty set. And this is this ancient doctrine of Creatio Ex Nihilo, where you try to create something out of nothing. And religion certainly tries it with limited success. Physicists have tried it, but again, there's always that, well, what happened before this? So in math, you kind of say, hey, these are the cards I have. I'm going to do this trick, and I'm not disguising it as anything, but you have to start with something.
But do you think that, so I mean, we have to have this sort of axiomatic start where we have to make this basic assumption. Do you think then that leaves too much room for error, though, that basic assumption?
Well, so here's the thing with math again. Math is completely agnostic. It allows this possibility of error, says that, hey, if you start with some other assumptions, you will get some other system of mathematics. So it's kind of hard to, every time you use mathematics, you come up with a model, and then that's the model. If it fits your idea of reality or the universe, that's great. If it doesn't, hey, try something else. So I think that's one of the kind of nice things that you might say. It's not really pinpointing things, but that's one of the advantages of the subject, I think.
Yeah, no, I think I completely agree. So I've written a bunch of questions based on not only the book, but some of the papers, the one you also sent me. There's so much work to discuss, but I tried to narrow it down as much as possible.
Sure. Yeah.
So you've already touched on the Creatio Ex Nihilo, just creation out of nothing. What I want to ask you is, why does the universe have patterns in the first place? I mean, why isn't it as amorphous or unstructured as we'd assume it is?
Yeah, I mean, that's a great question. And again, this is where questions like almost quasi-religious kinds of questions come in, where why is that? Why don't you just have something completely undifferentiated? Now, physicists will tell you that it's because of the weak force and the strong force and all those other effects that started occurring right after the Big Bang. And that's just one theory. There are many other theories. Religious people will say, hey, well, that's what God did. He started with the chaos and then got the universe out of that. Mathematicians will look at it a little differently. They will look at things like randomness and, say that, hey, even out of randomness, a simple kind of algorithm, even if there's a little spark somewhere, something going on, you're going to somehow see some structure from that. And that's kind of the essence of chaos, which isn't the same thing as randomness, because chaos shows you that even when things look completely random, some things are accumulating or occurring, or there's some sort of phenomena which causes some order, some structure. And so that's, mathematics is full of examples like that. So I think that's the kind of, the spiritual side of mathematics, if you will. But this is a question that's more philosophical rather than something that can really be answered by any of these fields, I feel.
No, I agree. And at some point, I mean, this is far down, but I also wrote, if the universe is constructed by math, which I think we can go into more detail if you'd like prior to answering this, but then why is it so inaccurate mathematical as well, for the most part? We often find that there's a finiteness and there's randomness. How does all of this work? I mean, is it infinite? Is it purely random? Is it something that's purely philosophical, or do you think we have the capacity to answer these questions?
Well, I'm honored that you would think a mathematician would be able to answer these questions. So, great theologians and philosophers and so on have tried. So let's see what we can talk about in terms of that. Why is it? Well, you asked a lot of questions, so let's just pick one. Maybe you can just pick one and
let's start with first. Let's talk about how a universe can be constructed with math.
Okay, so that's when you say the universe again. I would start with just nothing, as I do in my book, and say that okay, from nothing you can actually construct the numbers. And that's pretty standard. It's a something that can be done quite easily using set theory with a minimal amount of assumptions. So you have the numbers, let's say, And then the question comes about geometry. And already you're on, kind of tricky ground, because if you look at religious texts, for example, God creates the universe, Brahma blows out the universe in one breath, and things like that. And there's always an assumption that empty space is already there. And that you're creating, it's almost like a stage, a matrix of points. And so God is filling this empty space. But the question is, how did that empty space come up with? Where did it come up from before any construction has taken place? And so I think mathematicians are good at showing how this empty space can actually be constructed. And you can do this with points. If you have points, if you had an infinite, and we are coming to the infinite question, if you have an infinite number of points, then you can create a line, and this line can be extended in both directions. And if you have a line, maybe you can duplicate it and then create a plane from that. And once you have a plane, you can stack these and you can create 3D space. Physicists are actually pretty, they're not as cavalier as people in religion about empty space, because they actually point out, like, the Big Bang is not it's not the creation, it's not an expansion, it's not a Big Bang in space, it's a Big Bang of space. So space is actually being created. So things are starting with a little point, and then things proceed from there. And as time evolves, so is space actually being created. And in terms of space, what is space? Well, it's a medium. I don't know what you would describe it, but it's a way of differentiating things. So it's very tied in with distance. But that's the kind of view that physicists would have. The problem arises in terms of finiteness and many other things. If you start talking about finiteness versus infiniteness, what evidence do we have? Well, as far as we can tell, this is something, as far as we can tell, we don't know even whether our universe is actually just the space aspect itself, whether it's actually curved or it's completely flat, like Euclid would have had it. The best experimental evidence suggests that it is completely flat, up to a small percentage of error that might say it's curved. Notice that if it was curved as a sphere, it would have to be finite. A sphere has a finite amount of volume. If it's flat, like a cube that's expanding in all directions, then it would be infinite. Now, whether it's infinite right now or in the limit, that's another question. So you immediately come up with all these questions that kind of make the discussion very murky. But the nice thing about mathematics is that it makes you think about all these things, infinite versus not. And even in terms of a sphere, which is finite, you then have the question of, okay, space itself, is it corpuscular? Is it quantum? Just little pieces which are discrete. Is it discrete in some sense? You jump from one point to the other and there's nothing in between. Or is it continuous? In which case you have a continuity of space. Similarly, time. Do we experience time in tiny kind of quantum instance? Or is it a continuous flow, like a straight line? So there are models for all of these, and people have come up with nice theories for all of these, but it's very hard to actually decide which way reality has been patterned.
As something that, I mean, I know you start with this, with the basics of an empty set. And a note I made at that point was, what to you, I mean, it's pretty obvious, but just for you to explain it was, why is the empty set an equivalence to physical nothingness, let's say? Why would you start with that as your basic assumption?
Well, that's what mathematicians do when they're constructing the numbers. I don't think they are really making this equivalence that I've tried to do in this book, which is, I have to apologize for being glib a little, perhaps. It's a finesse. It's a trick because all of these things, all of any creation theory always has a trick to it.
Yeah.
So I make that quite clear in the beginning. I'm a magician performing a trick. So yeah, so you have to make that leap of faith that the two are equivalent. But in some sense, nothing is the empty set is the closest thing. It's the translation of nothing into mathematics. That's I can't think of anything simpler than that. So that's the equivalence. That's my defense.
I guess even the question is pretty difficult to ask because for me to even say physical nothingness is almost very oxymoronic anyway.
Yes. There's a paper I've read which has like 11 different stages of nothingness. There's physical nothingness, then there's mental nothingness, there's a nothingness where there's no thought or and there's a nothingness where there are no laws. So you get more and more progressively less and less in this nothingness. So which one are you talking about? We need to go through that entire list, I guess.
So at some point you mentioned the role of nature in your model, and how is this word nature defined differently in this context, and why did you go with this sort of definition in mind?
Yeah, so here I was trying to create the whole universe using only mathematics, and I did reasonably well with the numbers, and then the geometry also was okay. If you have a point, you can kind of do that. But then I got stuck. Empty space is fine, but in terms of really filling it with anything, well, mathematics is very abstract, as I said, and it's impossible to just use mathematics and come up with something that's actually physical or real or concrete or tangible. So that gap cannot be bridged by mathematics. You can't even create a little particle just using mathematics. You can create a model for it. You can create the numbers for it, the coordinates for it, but not the actual particle. So that's where nature came in. I had to have something, some way of progressing, and so I chose nature, which in Greek it's the word physis. I think that's how it's pronounced, and that's where physics comes from. But it's also nature. It's the mythological form of nature as Mother Nature and so on. So it's a very interesting term, which can, depending upon your own beliefs or what you add to that term, it can either be a kind of religious term, a goddess, a mythological figure, or it can be purely scientific. I just take nature. I mean, this is my definition. I'm trying to prove that the whole universe basically is a model for mathematics, that there's some mathematical truth that drives the universe, and the universe is a manifestation of that mathematics. And so in my terminology, nature is something, the definition of nature, which is very hard to do, to define nature. But in my terminology, it is what is a force that converts mathematical design into reality. So I kind of have to leave it at that. But there is this, it's like a contractor. I give you the plans of my house and you build it. Now, I don't really care how you build it, if you use miracles or something, or you use pure science, something that's explainable by science. But I'm just going to have to assume that there is something that actually converts mathematics into physical reality. And that's where algebra comes in, because I use algebra as the language with which I can specify what I want. And nature follows that and is able to build things.
Yeah, you see, you used it. So at some point in your paper, you wrote, nature is the force that converts mathematical blueprints into physical reality.
Right. Yes. Yeah.
I don't know do you want to briefly just touch on like a brief summary of how you go about with each, because in each chapter, I love the way you break down the book into sort of the 7 days, kind of like the creative story. And then you sort of go into each mathematics. Do you want to give like a brief synopsis of what you do there?
Sure, yeah. So the first day one, is, and these days are capital D because, they're the 7 days of creation according to Genesis. So day one is when you start with nothing and you build up the numbers, and the numbers then you build up arithmetic too. Like what do these numbers do? What are they good for? So you build up all of arithmetic, and we're not just talking about 1, 2, 3, 4. You can also start building up other numbers like fractions and irrational numbers and even complex numbers. And the complex numbers, which involve things like the square root of -1, they come in handy in day 2, which is geometry, because the way I present numbers in this book is to motivate people. I give them kind of personalities, so
Yeah.
they actually interact with each other, and they're entities of some sort. So in day 2, I'm building geometry, and again, I need to start with something, and that something is a point. So once you have a point and you can reproduce it, as I was saying before, you can create lines, you can create planes, and so on. And if you just had the numbers, one, two, just the real numbers as they are called, you could just fit them very easily on a straight line. So the way I motivate geometry is that these numbers want some place to actually have a house or a condo, as I call it. Each number needs its own condo unit. If you just had the regular numbers, you just have a straight line. If you have the complex numbers, all the condo units get filled with just the numbers that we know of. So when you start taking the square root of -1, you get these other numbers and they don't fit in anywhere. And that's when you have to come up with a second dimension. So that's what motivates a plane. So that's day 2. And in day 2, all sorts of ways of creating space, including, and this is something where I use the idea of crocheting, because you can actually see how these curved spaces can be created with crochet. So day 2 looks at all these different kinds of spaces. And then day 3 is algebra, where now you have nature and you're actually telling nature, hey, I want this, this, this. And you're expressing these things with algebra. And then the next thing is patterns. So day 4 is building patterns. And this is something that is often people have probably seen things about symmetry and things like the golden ratio and a lot of stuff like that. And where does that come from? And the way I'm presenting things, it's almost like nature is fascinated by some of these patterns and then decides that she wants to keep using them. So day 4 is about patterns, and one of the things that we really get into is fractals, like very complicated patterns that are much harder to generate, but with very simple formulas you can generate them.
I actually wrote a note saying, sorry to disturb you there.
Yeah.
It says, talk to me about fractals and tell me what they tell us about the complexity that arises from simplicity.
Yeah, that's a great question, and we'll still be talking about it like 20 hours from now, probably, if I really get into that. But the easy answer is that and there's so many examples. If you have a triangle, for example, just take a triangle and then take out its middle 1/4. So one triangle, you can break it up into 1, 2, 3, and then central piece. If you take that out and then you keep doing that for all the triangles that are left, you'll get something that's if you kept doing it an infinite number of times, you'd get something that you wouldn't be able to tell whether any part of it was actually shaded in, whether any part of this had an actual area. And that's the quintessential property of a fractal. You can't tell which dimension it is in. Is it a 2-dimensional triangle still, or is it something else, because you've taken out all the area. And the other thing you'd notice is that there's a lot of self-similarity. Like the same pattern keeps getting repeated at different scales. So these are the two defining characteristics of fractals. And the fractals that we encounter in nature often occur because some sort of event or other process is occurring over and over again at different scales. And the best example, I think, is about the tides that come in and keep chipping away at the seashore. So there'll be little laps of water that just take away a little bit off at a time, but there'll also be giant waves that break off chunks and rocks, and maybe the occasional tsunami that really does a lot of damage. But if you think about all these effects cumulatively over several centuries, then what happens is you get our coastlines. And because of the way this force has been acting at different scales, big scale, macro scale, and a micro scale, you'll find that there are similarities that occur in terms of the pattern that you find. In other words, classical thing is if you take a coastline and expand it, magnify it, you might see traces of the same kind of shapes at different scales. So that's, again, an example of a fractal. So a lot of things occur in this way, in this evolving way. And you can identify fractals by this self-similarity. Notice that all these effects, all these, the tide coming in and going out, it's a very simple phenomenon. You can express these in terms of very simple formulas. And they then give you this extremely complex surface or coastline or whatever. So that's, I think, a good illustration about how very simple things in mathematics can lead to great complexity.
Yeah, and I think it's great to start with that understanding, because then it can go forward to sort of explain the creation of life. And in your view, I mean, particularly with the context of this podcast, how do we get from that, from sheer simplicity to the complexity of life, and thereafter maybe even consciousness? I don't know if you.
Yes. Yeah. I mean, that's again, I don't think, whatever I've read on this, I don't feel that it's quite, airtight yet, but I think there have been a lot of strides made in terms of questions like so what I feel is true is that mathematics gives us a model. It doesn't actually explain how life is going to come about. It just gives us this idea that you can get complexity from very simple processes. It also shows us how things can happen in what is called an emergent framework, that some of these patterns just emerge. You expect that, hey, things need a father figure or a god or someone to be sitting there and saying, okay, I'm going to do this. But a lot of what we see is just the way things are, the way things have evolved, and that's why things look the way they do. Like mountains, for example, the structure of mountains, landscapes, they're all very fractal. And that complexity that we see has come through centuries of evolution, waves and wind and all of that occurring. So that's, again, an emergent phenomenon that no one actually sat down like an artist and said, I'm going to paint the mountains this way. It just happens. So the best that I know of in terms of consciousness or life is that these are labels that we attach to a certain type of complexity that might have emerged from these repetitive phenomena. For example, if you have the right kinds of chemicals or right kinds of ingredients for cellular structure, and you keep churning them over and over again together, there are millions of reactions that are taking place. And if this goes on a large enough number of times, maybe you would start seeing molecules that are tending towards what we call as life, but which are really more and more complex molecules. And so that can then, progress in a way that you would eventually come up with this greater complexity that we would label as life or consciousness.
Yeah. And do you think that that sort of labeling takes place at a single point, or if it's kind of just blurred out throughout time?
Oh, that's a great question. And there are, again, being a mathematician, I can give you a mathematical model for that. Yes. So now there's a name for that phenomenon. I can't remember the name, but the mathematical idea for this is, you start counting 1, 2, 3, 4, and if you keep doing it, you will eventually get to infinity. But at what stage does that break off occur? Can you actually say, hey, up to here is finite, and then things become infinite? So it's that kind of conundrum that there's actually a name for it, and that's the same kind of idea that you're asking me.
I'll try and check out what that is after this. But yeah, I think it's intriguing because I mean, when people think about the universe, there's often those handful of questions that always come up. I mean, why is this universe here? Why are we conscious? Certain other things like free will. Are these topics, other than the universe itself, are consciousness and free will something you give a lot of thought from your mathematical perspective?
Not so much actually. I haven't given thought to it, but actually, interestingly enough, what I've been writing now is a memoir, which involves my mother, and she was extremely intelligent and so on, but then she ended up getting dementia, and so it tracks that. And some of the things that I've been looking over the notes that I wrote for that, and some of these questions come up over there, like where does one thing that was fascinating to me was how malleable consciousness is.
Mm.
Now, this can be both in a good way and in a bad way. The good way first is that in terms of learning mathematics, people have shown that your brain is extremely adept if you use it in the right way. So they've documented, for example, cab drivers in London that have to pass this, you've probably heard of this, that have to pass this very difficult test and have to keep all these routes and so on in their minds. And they're able to do it. And it's a very mathematical kind of thing. And these people aren't trained, but they're able to negotiate the mathematics that's inherent in this. But then when they stop it and they no longer have it, then they lose that ability. So your mind is very adept at, if you train it the right way, being able to do this. What I noticed with my mother was that one of the signs with dementia is that you become very paranoid. But there was always a logic to her paranoia. She would interpret things in a kind of different way and say, hey, this plus this gives me this. It's almost like it's again that axiomatic structure. If you feel, for example, that the CIA is, looking at you and tracking your every movement, if you start with that assumption, then you can actually fit in a lot of things within that framework. And that's perfectly mathematically correct. We mathematicians would applaud at how you're doing that. And this, unfortunately, is why fake news is so hard to eradicate, because, again, you twist the axioms a little bit, and then you can just fit everything quite nicely and interpret everything in terms of the kind of conclusion that you are most comfortable with.
Mm.
So there is the idea of consciousness. I'm sure if you really analyze how it works, there is some axiomatic structure to that. And I would think that, I don't know if there's a big thrust of mathematicians looking at this, but it would be very interesting to see what they said.
Yeah, no, I think that's exactly what's happening, because nowadays it seems that the most prominent sort of viewpoint on consciousness is that of Bayesian brains. And sort of viewing this brain as almost a statistical organ that's taking in prior information and regurgitating these posterior conclusions about the world of reality. Do you think that's sort of an appropriate starting point?
Yes, I think certainly probabilistic stuff is how things work. Yeah. But what I was I mean, exactly. So there are these different ways that you can proceed, and so there's going to be a certain amount of people that will choose path A rather than path B, and these are both interpretations of something that happens. So I don't know if that's how I'm thinking about where the probabilities come in.
Yeah, it's pretty much along those lines. If we just give a certain amount of credence to each decision based on our prior experiences overall. And it seems to be doing a lot of work, great work, even within psychiatry, which helps then solidify its validity overall, because you can kind of tell how certain mental illnesses are fundamental errors within priors rather than the posteriors, and vice versa. And it does have some explanatory power in that regard.
Yeah, but the thing that is hard is that I also noted was, once these ideas get rooted in, it's so hard to root them out.
Yeah.
It just is extremely difficult. So I don't know if that's a function of your brain, creating pathways that it just get embedded in that and just have to keep going that way. Because I think the cure, if you want to call it that, is basically choosing a different path, and
Yeah.
that seems very difficult.
It is quite a tough one overall.
And I'll just say one thing related to that. That's one of the reasons why mathematics is such a difficult subject, because to learn for so many, because they kind of a lot of people will go into this failure mentality that they will say, hey, each time I get something wrong in a test, it's because I can't do mathematics. And that kind of self-affirming cycle just makes these grooves deeper and deeper, and it's very hard to get out of them. If you have a different mentality that, hey, I didn't do well in this test because I didn't work hard enough on it, then that's the kind of way that you can actually get better at it. So
I think my only problem with the Bayesian brain hypothesis for consciousness in itself is that we often tend as humans to take the current mathematics and apply it to consciousness particularly. For example, many years ago it was pumps and vessels, and we kind of take that framework and utilize it. So I think that when we do, I mean, perhaps yours is correct, and maybe this approach can be fine-tuned into consciousness research somehow. Do you think that's a possibility?
I'm not sure I understand your question.
Okay, so this mathematical framework that you've got, do you think people can utilize it and go forward with some consciousness research? Is there a practical implication?
Well, I would guess that there's axiomatic structures to so many things that like economics. There's many axiomatic theories of economics. You assume that all people or all participants are working for their own gain and blah blah blah, and then you build up what's going to happen. And this kind of structure has been used in other fields as well. So I would guess that you would probably have something like that for consciousness as well. I haven't thought about it enough, but that's my gut feeling.
Overall, so within your book, I mean, at some point you also go into sort of the practical implications of such a view. I mean, there's this move away from a theology, but into this sort of mathematical framework. So there are sort of practical implications to it. Do you want to tell us about like some of the liberating aspects of seeing the world within this mathematical framework?
So I think the best thing for me, at least, is that it makes it so that the world is logical. You want things to be logical. So for me, that's very comforting. That okay, everything is happening for a logical reason. I think that's one of the things that draws a lot of people to religion. For instance, they want an explanation. Why did this happen? And for me, randomness is a very good explanation. It depends on whether that's personally satisfying or not. For me, that is more satisfying than saying that, hey, somebody, didn't like what you did in your past life, and therefore they're punishing you now. But so I think that's one thing. The other thing is that if things are really based on mathematics, then this idea of the unreasonable effectiveness, that becomes clear cut. Everything is based on mathematics. So obviously mathematics would then do things very well, explain things very well. So that's another kind of advantage of how this framework, thinking in terms of mathematics being at the center of the universe, how it helps. And you can also talk about some of the questions that you already brought out were, what about why are things so imperfect? And for that, we've already talked a little bit about the fact that we don't have infinite resources. We don't have, nature cannot, the mathematics is always rooted in the infinite, and then you somehow have to dumb it down and make things that are finite. So thinking about that also kind of explains some more that it's not going to be exactly right. And the last thing is that, okay, you have a contractor, and I don't know if you've ever had any work done in where you live, but anytime you're working with a contractor, you can expect there to be some grief involved. Things will not go right all the time. The contractor will want to put in their own little tweaks or whatever, or mistakes. And so that's again certainly something that we see a lot of. We see little changes in DNA or things that aren't quite fitting into the pattern. So that again explains why this thing can happen.
Sort of the glitches in the matrix, kind of.
Yeah, exactly. And I always think of there's something about carpet weavers purposely putting in a little glitch or a little error so that it's almost like a signature that they're putting on it. So that's what nature is doing. She's playing with us a little bit.
Mm. And then tell me, have you then given some thought to the teleos of this mathematical universe? What is this, or what is the overarching goal, or is there one?
Overarching goal.
Is there a goal directedness to this mathematics? It doesn't have to be sort of a religious one, but more of a, where is this math headed?
Yeah, that's like, we don't even know about what this is first. Yeah. So I don't think I know enough about the animal, so to speak, to know what it's aiming for. So that kind of dichotomy, or that duality, whether mathematics is something that we think up in our brains, or whether it's something that just exists by itself, that these numbers start with nothing and create themselves, and the rest of mathematics follows. That's still an open question, obviously. But if you look at it in the second way, that this is all happening because there was nothing, you don't expect there to be a goal somehow. That's my gut feeling. That if you're really using randomness to justify the existence of mathematics, that things are just developing by themselves, then it's once again like that emergent phenomenon where there is no artist who's really creating this tableau. Mm-hmm. It's just happening because of the way things are unfolding. And I feel uncomfortable saying that there would be a goal, because that always calls into question whether there is someone who is actually orchestrating this. So I'd rather stay away from that.
Yeah, that actually would be a great idea for a second book, a follow-up to this one. I mean, sort of like a big crunch of numbers, or a big big ending to this whole story.
Yeah, right. Well, I just need another 10 years, and then you can interview me then. So, yeah.
Tell Manil, what really absorbs you at this point in your life? Like, what work really gets you excited within the mathematical sphere, or even science in general?
So right now I'm trying to write a piece that's in my research field of finite elements, which is a method that was developed by engineers, and they basically, if you have a structure like a bridge or even an airplane or something like that, you want to know what kind of stresses can this structure can withstand, and you want to make sure that tiny cracks don't bring the whole thing down. And so so mechanical engineers have been figuring out ways to, first of all, model this using equations from physics, and secondly, solve these equations. And you can't really solve them exactly, you can only do them approximately. So they came up with lots of methods to do such things. And one of them was, okay, we'll just replace this structure by various springs that are attached to each other. And then we'll kind of, figure out what happens with these springs. And then that would give us a good idea of what would happen with the structure. And they were able to do this all very mathematically. And this was in the 70s or so, even before that. Then in the 70s, mathematicians started taking a look at this, and they started putting it in very mathematical forms. And they said, okay, you need this, you need these abstract spaces, and then you can talk about a solution and its approximation, and you can see how well the approximation converges to the solution if you use enough computer power. So that's what the mathematicians did. They made it very orderly, and as they were doing that, they also found that the engineers had been using all sorts of tricks and so on to make things conform to the experiments that they were seeing. So, you have this model, you find the solution, and then you compare it with what actually happens in practice. And, if it doesn't compare very well, you use these little tricks and so on, and then you get the approximation to be much closer. Now, the problem is that around the mid-70s, there were a lot of programs, commercial programs that were developed. And these commercial programs used all these tricks and everything. And they turned out to be very useful, and they were used in, almost anything that you can think of. And they still are used right now. So these are called the legacy programs in this field, in the finite element field. The problem is that the mathematicians, when they started finding problems, this was a little later, so it wasn't easy to then go back and fix these programs. And there were many advances that mathematicians came up with, and that's kind of what I was, involved in as well. And over the years, these advances have been used by researchers and so on, but they haven't really percolated down to this ground level legacy programs, which are in great use everywhere. So far things have been going along pretty well, because the engineers can still do their fixes and so on, and things work reasonably well. Not great, but reasonably well. But now they're talking about having AI take over and, figure out, add that as a component to these programs so that these programs will automatically look at a structure and talk about which are the best ways to discretize it, where we should put more computer power, where chances of more action being seen are greater. The problem is that no one really knows how that's going to interact with the kind of fixes that engineers have been doing. The fixes are not democratic. You really need someone to know what to do and how to do it. So that's something that a mechanical engineer professor, a colleague of mine, just brought up, and so that's a problem that's very interesting, especially since it's like looking at this same work that I did many years, but now how does that actually? Where is it going to be used? How is it going to be used? Is it going to be used? So it just also illustrates how difficult it is for mathematical research to really trickle down and make the kind of effect that we would like, the kind of impact we would like, because certainly at a research level, things are fine, but when you go down to real commercial hardcore stuff, then there's still a big gap between engineering and math. So that's something I hope to be able to at least cast a little light on. So
it's sort of bridge that gap a little bit, because it's we even touched on it earlier when we spoke about how even though it's so mathematically structured, it's still so mathematically inaccurate when we look at reality, and that's sort of what engineering does with mathematics. It takes those inaccuracies and sort of applies it so well, where it's actually surprising to the mathematician.
Yeah, and the mathematicians, we can make our theories, and if they don't work, fine, no problem. If the engineers do something like that, the bridge collapses. So that's not acceptable. So it is a complete different way of looking at things. And a colleague of mine used to say that engineers think in terms of examples. So they'll keep giving examples. Hey, it works here, it works here, it works here. Mathematicians think in terms of counterexamples. So we immediately start thinking, hey, where will it not work? So we are the eternal pessimists, I guess. I don't know.
Yeah, that's actually a very nice way to think about it. I found that's something I'm going to actually document.
Yeah.
Any advice you give to sort of future mathematicians who want to enter the field for exciting areas within mathematics today?
Well, everything is being turned over completely topsy-turvy with artificial intelligence and machine learning. like even to give you an example, the kind of work that I've been doing, very like looking at structures, looking at what kind of refinements will give us what kind of results, how to improve convergence, and so on. There's a group that is now just saying, hey, we don't need any of this. What we're going to do is we're just going to pop in some examples, a whole bunch of examples into our machines and let the machines learn and basically figure out. And it's a pretty standard algorithm where if you put in many equations and figure out a bunch of solutions for them, then the machine is going to be able to learn and it'll be able to digest any other parts that you give it and just pop out the answer. So that's one train of thought. Now, fortunately, there's still a lot of problems in that, and I don't know if it could be perfected to the extent that it would be completely accurate. But if you start saying that everything can be done that way, then it's hard to predict where the excitement will lie. In the past, math has been traditionally pure math and applied math. And the applied math is the kinds of stuff that I've been talking about, that I've been doing. In terms of pure math, there are also issues. Like pure math is questions in number theory or questions like the packing of spheres and so on, all these very abstract questions that might not have an immediate application. And there also, there are now automatic proof theorem provers, automatic theorem provers. There are things that there are big databases being built where a lot of mathematical results are being codified. And these programs are able to then identify structural similarities between very different areas of mathematics. And they're able to connect these two and then come up with new theorems, or at least help people see new theorems. So that's going to be an issue. Like, okay, it's not going to be strictly your mental power anymore, but some of these new tools that we have. So the very questions that people will be thinking of might be really different.
Yes.
So I feel like I need to take a step back and rather than try to advise anyone. So I think the basics though are going to remain the same. You still need to know a lot of things in mathematics to be able to get to that level where any of this is going to be, going to make a big difference.
For someone who's not a mathematician, I'm always curious to know how rapid is the machine learning or AI mathematics, the mathematical field. How fast is it really growing at this point? Because it seems to us like as if this thing is just dynamically evolving at a rapid pace. Is this really the case? Are we getting that close to like such complexity that the average human will not be able to understand?
Well, okay, so certainly in mathematics there have been theorems proved that by machines, and the methods that they've used have been kind of opaque to humans. A few theorems have been proved. So it's like, okay, this is not what, it's very hard to kind of map it in your mind. However, what's also true is that there's certainly not that golden bullet as at present, because most of this is theorem assistance, proving assistance. They're not able to just function automatically. You set them loose and they'll prove all sorts of wonderful things. There is a program called Lean, Lean, and this is an automatic theorem assistant. And what this does is this is one of the places where people are spending a lot of time putting in theorems and building up this database. And the idea is that it'll be able to draw on this database and then prove things itself. Right now, though, if you want to prove something using Lean, it takes a lot longer than just proving it yourself. So it takes about, I don't know, somebody was telling me maybe 5 or 6 or 10 times as long, just in terms of programming all the steps and instructing the kind of giving the computer a way of, a way forward to how to actually prove this. So you have to keep assisting it right now. But so we haven't reached the stage where, the computer is going to be able to plug itself in, and the worst case scenario is all mathematicians are suddenly redundant. We haven't reached that stage yet.
Well, let's hope that it never comes to that, because I mean, it's always great for people like us to look up to people like you and read your work, digest it, and absorb it all.
Yeah, the question though that people have asked is, if you do get to that stage, and you have these machines proving theorems, wonderful theorems, would that really be something that we'd be even interested in? If we are not the ones that are making these conjectures, and if we are not able to fully even understand their proofs or appreciate them, call them elegant or anything like that, why would this be of interest?
Yeah.
Especially pure mathematics. Why would that be of interest? So who knows how things will progress?
That's actually a very fascinating thought. It reminds me of this. I don't know if you watched this movie called Her with Joaquin Phoenix.
Yeah. I watched part of it. Yes.
AI becomes so complex at some point that they have no frame of reference as to how to think about this thing or what to do about it. I mean, it would go beyond us completely.
I know. So yeah, well, I'll have to write a sequel then. But the AI Big Bang of numbers or something like that. The Big Bang of AI. But that we all know that's engulfing us right now, I think.
It is. It's very absorbing at this point. Any final words, Manil? Anything that you feel like were you left unsaid regarding the book or this journey into this mathematical universe?
Well, I think the main thing is there are two things. One is that what I just talked about. Would anyone really appreciate mathematics that has nothing to do with us? I think that's one of the joys of mathematics is that it's a puzzle, and I think all of us react well to puzzles. So it's something that should give you joy, and that's what I've tried to do with this book. Bring out those parts of math that I like the most and present them in a way that it's actually a story, so you can kind of follow it in that way. The one thing that people ask me is, okay, what should I do if I'm not a mathematician? Should I be reading books like that? And the data that I've been gathering from friends who, obviously feel forced to buy my book when they come to my reading, and then some of them actually venture into reading it, is that yes, it can be done. So that's a big relief. People who don't have training in mathematics but do have interest in it, which is a big if, they're able to just take it a little bit at a time and read it. There's very little formulas in it as such, but the thing is that there are ideas, and the ideas always take a long time to settle in. So the main thing is not to rush it. And I can say it's sort of like I came to literature a little later in life. So when I am confronted with something like Tolstoy, I read Anna Karenina like last year, and it took me a long time, but I enjoyed it. But it was like you have to know your limits, and I'm sure other people would be able to absorb it much faster. So I think that's where looking at this as a way of expanding your horizons and also having fun. So that's why I wrote this book.
Well, I think I can defend that, because as a medical doctor, I mean, we're not that ingrained in the mathematics, and we do basic mathematics, but it's not that intense. And for someone without that serious background in mathematics, it was an enjoyable read, and it's relatively absorbable within a single reading. I mean, I can imagine reading it more. I'd probably gain a lot more from it. But as a first time read, it was very well done. And thank you for your excellent work.
That's great to know. Thank you.
Tell me, why did you name the book Big Bang of Numbers?
Oh, so that's a good question. It's called The Big Bang of Numbers, and then there's a subtitle, How to Build the Universe Using Only Math. And the Big Bang of Numbers actually comes from an incident that occurred when I was an undergraduate, where we had this professor in India, in Bombay, now it's Mumbai, who told us about this saying by Kronecker, which said that God made the numbers, the rest all is the work of man. So God gives us these numbers 1, 2, 3, 4, and everything else.
Anil, is it not the integers? I think it's the integers.
Oh, the integers. Sorry. Yeah. Let me say that again. Yeah. Yeah. I knew when I said numbers, that's not quite correct. Okay. So yeah. So the Big Bang of numbers. The title comes from this incident that occurred when I was an undergraduate in Bombay, which is now Mumbai in India, and our algebra professor actually told us this saying by Kronecker, which is God made the integers, rest all is the work of man. And the idea was that, 1, 2, 3, 4, etc., they're God-given, and then we build everything from that. And then this professor showed us, he said that, I can do better. I don't even need God, because I can actually make all the integers myself, just starting with nothing. And he showed us this kind of almost a magic trick on how to do that using set theory. And so that's always stayed with me, because it was like, almost like a religious experience, you could call it. Like suddenly I could see numbers everywhere, and it was like creation. And that's the idea that I took into this book. Could I keep going? When it says that rest all is the work of man, of human beings, can we actually create everything using mathematics? You start with the numbers, and then, where does that lead to? Can you create the whole universe using that? So that's where the title of the book comes from.
I think, well, it's a beautiful book, great title, and hopefully in 10 years we'll be having this conversation about the Big Bang of AI, or wherever else the universe takes you, this mathematical universe.
Sounds good.
Thanks so much, Manil. Have a great day.
Okay.
Thank you so much
you
for your time.
Okay, take care. Bye.